In the next part of section 2, we're going to be looking at step functions in a little more detail. We saw an example of a step function when we talked about the greatest integer function at the beginning of this section, talking about our parent functions. And not every step function is the greatest integer function. There are lots of other ways that we can create a step function, and this is an example here. 2.5 says the U.S. Postal Service uses the following table when calculating the cost of shipping stamped letters domestically. Define and graph a cost function based on the table. There's two things we're being asked to do here. Number one, it says define. Number two, it says that we're supposed to graph. Now, what it is that we're supposed to define and graph is a cost function. And the definition for the function, when we say define, what we mean is to define algebraically. And algebraically is going to be using an equation and the domain. And at this point, we don't have either of those things. We don't have the domain, nor do we have the equation. Now, to help us understand the domain, we would want to look at a numerical representation for this particular data. And this is data that was pulled from the U.S. Postal Service website. By the time you see the video, it could be slightly outdated, but nonetheless, this is something that they do keep updated on their website. And the table that they've provided is a little tricky to read because of the way that it is presented. It says weight not over, and that means that we have to be really careful about the type of things that we're considering. So my first thought is for us to actually make another table in place of this one, so that way it looks more like what we're used to working with in class. So we would say the first column is going to be the weight of whatever it is that you're going to be mailing, and then the second column will have that be the cost. So I'm going to pick some values that would be, I guess, fairly typical of going in and sending a piece of mail. Maybe something like 0.4 ounces. Now 0.4 is not bigger than 1. It's not over 1. It's less than 1. So where it says not over, we have to see that what we're dealing with is something that's not over 1. So therefore, we should be paying 49 cents to ship it. So the cost will be 49 cents. If I pick something that weighs 0.7 ounces, it's also going to cost me 49 cents. If it weighs exactly 1 ounce, well, 1 ounce is not over an ounce, it's exactly 1 ounce. So that should also still cost 49 cents. But if I go over 1 ounce, say I go to 1.5 ounces, I want to ship something that weighs 1.5 ounces, then I'm no longer going to be in that first category. Then I'm going to be in this second category because my weight is not over 2, but it was over 1. So then that's going to cost me 70 cents. And then the largest weight that I could potentially have that would cost 70 cents would be 2 ounces. So 2 ounces would get me 70 cents as well. Now this particular table is designed for only particular weights. So they have a whole host of tables available depending on what kind of object you're trying to send, how much it weighs. So the largest value that this particular table will calculate for you is 3.5 ounces. Anything over 3.5 ounces, this table is not going to work. So this is going to cost you $1.12 if you're going to send something that weighs 3.5 ounces. So I want to take this information and I want to try to graph it. I know the first thing on the list is the algebraic definition, but I think it would be easier to get a graph first, then we can look into writing the algebraic definition. So I want to make a coordinate grid, and I only need to focus on the first quadrant. and I really don't like where that's at. Let me scoot it over here a little bit. Since everything is positive, we'll just focus on the first quadrant. And also, because we understand that the largest weight that we can have is only 3.5, then I really don't need to have a tremendous amount of values on the horizontal. 1, 2, 3, 4. That should be sufficient. And I'm also going to go ahead and label the horizontal axis using the unit OZ for ounces, and that's standard. Whatever's in our first column goes with the horizontal. Whatever's in the second column for our table, that goes on the vertical. So I'm going to put a $sign up here for the vertical. We're talking about cost. And on the vertical, speaking of the vertical, I need to go all the way to at least $1.12. I don't really want to go by pennies, so let me go by dimes when I do this. 10, 20, 30, 40, 50, 60, 70, 80, 90, $1, $1.10, and that should be $1.20 right there. So 1.20. And I'll just label all these going down. And this would be a good time if you wanted to pause the video and work on making your own, and then we can get together once you're done. And then I can't forget 0 down there. So now let's take a look at the graph. So for the graph, I'm going to use the points that I already have. I know that 0.4 is supposed to cost me 49 cents. So that's going to be, yeah, about that point right there. And 0.7 would also cost me 49 cents. And 1 is also going to cost me 49 cents. But there's a whole lot of other weights there that would also cost me 49 cents. So I can connect these together, connect them with a line to help represent all of the points or all of the weights that would be costing me 49 cents. But notice that I've stopped short of 0. 0 from the horizontal axis right here. I stopped short of that. And the reason why I stopped short of that is because it doesn't make a whole lot of sense to have something that weighs 0. Even if I was to go into the Postal Service and say, I want to mail a package of air, the package itself still weighs something. And I know the air weighs something as well, but the air weighs so little that it might not even register. But the box itself, or the envelope itself, will have some weight. So 0 as a weight doesn't really make a whole lot of sense with this situation. So I'm going to put an open circle at 0, and that's what I can connect the rest of those to. And this is going to represent everything from the first row of that table that I pulled from the U.S. Postal Service website. So going to the second row, we're looking at all of the weights that would map to 70 cents. What's going to cost 70 cents? Well, the easiest way to do this is to go to the end of the 49 cent line and go straight up from there until you get to 70, and you're going to mark an open circle right there. And then you know that 1.5 is going to cost 70 cents, and we know that 2 ounces is also going to cost 70 cents. So just connect a line from your open point all the way to that last close point, and now you've represented every single weight that would cost 70 cents. So now go to the end of that line, go straight up until you get to 91, and you'll want to put an open circle there. And for this one, we have to realize what the pattern is. So the pattern is that everything starting from that open circle all the way until you get to a weight of 3, everything there should cost 91 cents. So we'll start the open circle and we'll measure all the way, not measure, but we'll mark with a line all the way to 3. And then the final one we know that 3.5 is supposed to cost $1.12. And then going right above 3, I can put an open circle at $1.12, and then I can connect the line. So envision that these are all horizontal straight lines. It's the best I can do here with this technology. And this gives us a graph for this cost function. Now for defining the cost function, I want to be able to define it algebraically. So I need a name. And in class we typically use F, G, H, and these are sufficient names. However, in this situation, I don't want to just do a generic F, G, or H for the function name. I want to do something that's a little more meaningful. At the end of section 1, there is an example, specifically example 1.20, where we talked about area and an area function. And I used capital A in that example because capital A made sense with this being an area function. It calculated area. So for this particular problem, we're talking about cost. It's a cost calculating function. So it seems only natural to use capital C for the name of this. So that's what we'll use. And the domain for this function is not going to be all real numbers. It's going to start at 0, and as we discussed, it's not going to include 0, and it's going to go all the way until we get to 3.5, including 3.5, because that would be the largest value that this table will handle. And these are going to be the values that will map to real numbers. This is just a standard convention when we write it. And this will be given by, and then now we have to write the equation. So the equation is going to be called C of x. But C of x will need to be written as a piecewise function. And this piecewise function is going to have 4 pieces. One of the pieces goes with the 49-cent value. One piece goes with 70 cents. One piece goes with 91 cents, and another piece goes with $1.12. Now, we need to make sure that we specify which weights specifically go with those. So that's when we would say, comma, if, and we want to specify which values will always cost 49 cents. Which weights will always cost 49 cents. So anything that's bigger than 0, any x value that's bigger than 0 will cost 49 cents, provided that it is also less than or equal to 1. So that's the condition that's necessary for us to say that it costs 49 cents. And we can use the same pattern, do the same thing for 70 cents. That's going to be 1 less than x less than or equal to 2. So any weight that's between 1 and 2, including 2, would cost 70 cents. 90 will be between 2 and 3, including 91, and then $1.12 will be any weight value between 3 and 3.5. And that gives us the algebraic definition for this function.